Okay, so this time we're going to be talking about, let me make sure I'm recording. Yeah, okay. So this time we're going to be talking about word representation in text classifiers. Um, up until this point, we talked about bag of words, where bag of words is basically, getting a one hot vector that we look up and then we add them together, um, get weights, multiply by weights, and calculate a score. The features are based on word identity, and the weights are learned using something like the structured perceptron, as I mentioned last time. Um, so if we look at what is missing in the bag of words models, um, we talked about several things that it was missing. We talked about it missing things like conjugation or compound words. We talked about it missing handling of word similarity. We talked about it missing handling of combination features, so things like love to don't love and hate to don't hate, and also handling of sentence structure. And so this time I'm going to talk about how we handle a lot of these things, not all of them, but a lot of them. So we're going to talk about subword models that allow you to handle this rather easily and elegantly. Word embeddings, which allow you to handle various varieties of word similarity. How we implement and use neural networks, which allows us to learn combination features. And then this time, we're not going to talk about sequence models. That's what we'll get into next time, but that will handle the sentence structure. So first, I'd like to talk about subword models. So these are something that's used in virtually every large language model nowadays, but it doesn't really come to the surface. So you might not hear about it very much unless you've had to go in and look at the details. So the basic idea is what we do is we split less common words into multiple subword tokens. And the way this works is if we have something like the companies are expanding, that would split into the companies are expanding. And one important thing here is we have underbars or some sort of special character here. And the reason why this is important is because that allows us to have a reversible split. So what we can do is we can split up according to whatever our splitting algorithm is, and then we can unsplit by deleting all spaces that are followed by the special token. So this is a very convenient feature. Previous tokenizers did not have this, but you really, really want to have this, and if you want to use a practical application. So the benefits of this are basically that we can share parameters between word variants and compound words. So for example, if we do this, we have expanding. And so we can use the same word embedding for expand, regardless of whether it is followed by ing or not. And then we can have ing be like something special that converts it into the present progressive. Note that this doesn't always work. So here we split compan and ease. So we didn't split it into company and ease. So there are limits to this. And in English, this isn't a huge problem because the conjugation or morphology is very simple in English, but in other languages, it can become a pretty big problem. This can also reduce parameter size and save compute and memory. This is really important because there's lots and lots of words in English. Does anyone have an idea how many words there are in English? No? It's kind of an ill-defined question, isn't it? Like, how do you define a word? I can make up words all the time, and I can turn nouns into verbs all the time. So you can come up with a verb for turning nouns into verbs called verbing. Uh, and you've probably never used that before. Many of you have never heard it before, but you understand what it means. So yeah, it's tricky. But if you just count up the number of words by dividing them by spaces, you can get millions of unique words. And that's a problem if you need to learn parameters for all of them. So there's two common ways of splitting words, and it's not really important which one you use. They both result in similar performance. But the first one is called byte pair encoding. It's very simple. It's so simple that you can implement it in like tens of lines of Python. And the way it works is you incrementally combine together the most frequent token pairs in a corpus. So basically, you start out. I know this is very small, but you start out with um, the vocabulary in the corpus and the counts of the vocabulary. And so if we have like low with a count of 5, lower with a count of 2, newest with a count of 6, etc., we can then find the most frequent character pairs. So here, the most frequent character pairs are ES, which has 9, ST, which has 9, T, end of word, which has 9, and then WE, which has 8, et cetera, et cetera. And so based on this, you just can randomly pick among the most frequent character pairs. And that will result in ES being merged together. And so now we get a new corpus, basically, that has ES merged together. And we calculate the statistics again, and now we have, combinations like this. So we have like EST, which also is very frequent. And so we can combine that together, and now we have EST as kind of a suffix. So this is, like, as I said, this is so simple that you can implement it in, tens of lines of Python. So there's an example here of how we do that if you want to take a look, but that's the basic idea. The other method that people use is based on unigram models. And unigram models are a very, very simple method for language modeling, which we're going to talk about in more detail next time. But basically, a unigram model is a model that calculates the probability of every word independently and calculates the probability of a sentence based on the product of the probability of all of the words in the sentence. And so what you do is you try to pick a vocabulary where you have a given vocabulary size. You have a limit on your vocabulary size. Like you can only have 32,000 words in your vocabulary or 32,000 subwords in your vocabulary. And based on that, you try to do the combinatorial optimization problem where you find the best vocabulary that gives you the highest probability given that constraint. The way you solve this problem is using something called the EM algorithm. This used to be very mainstream in machine learning, but now I don't know if it is. How many people have taken a class that covered the EM algorithm? Okay, so it's still mainstream enough that we get like 1/3 or 2/5 of the people raising their hand there. But basically what it does is it calculates the probability of all of the vocabulary items and then it calculates the probability of the vocabulary items given the unigram model, then re-estimates the unigram model given the counts of those items. So it's an incremental algorithm. The details are not super important. And then based on this, you find the segmentation of the input that maximizes the unigram probability. So you find the segmentation that would maximize the probability of any sequence. There's a bunch of different ways that you could create things like this. The kind of standard or like OG example of doing this is a sentence piece. And it's a highly optimized library that makes it possible to train and use BP and unigram models very easily. And you can run it on the command line, just using these commands, or you can also do Python bindings. And there's also an example in Hugging Face. Apparently, I think I saw just yesterday or this morning that this got 10,000 stars after 6 years of being out. So congratulations to the sentence piece authors, I guess. So some considerations. Using subword units, there's a big consideration of multilinguality. So when you're using subwords, they are one of the biggest, this is one of the biggest downsides when you use a multilingual model. And the reason why is because infrequent languages, languages that don't appear very much in the corpus that was used to train these models, get very highly oversegmented. So I don't have an example in my slide. Let me see if I can find an example very quick. Okay, so here is the tokenizer. There's also a site that you can use to check the tokenization from a GPT model. So if I take this and put this in here, this is OpenAI's large language model. Large language models, sometimes referred to as GPTs, process text using tokens. And you can see that these are the tokens. Almost everything except GPTs was just like a single token per word. But yeah, almost everything other than GPTs was a single token per word. So now let me translate this using Google Translate into my favorite example language to use is Myanmar or Burmese, because it is a national language. It's used by a lot of people, but it's not super frequent on the internet. So this is Burmese. I can't read this, so I can't tell you if it's right, but I know that OpenAI is right. Uh, But if I remember, so look here, we had 58 tokens. Presumably, if Google translates half decent, this will be the same content. It'll be the same semantics between the two things. But if I copy paste it in here, that's 617 tokens. And so what does that mean? It means two things. It means that you're not going to get as good modeling of this language because all the tokens are going to be split up, and the model is going to have to work extra hard to kind of get the semantics from these very split up characters. The other thing it's going to mean is this is 12 times more expensive than processing the English, right? Because there's 600 tokens when you had 58 in English. So this is a pretty big problem for multilinguality. And this is the GPT-4 tokenizer. So it's, a tokenizer that was trained on lots of information. Cool. So the workaround to this is to upsample less represented languages. And so what a lot of places do is they calculate the tokenizer data from data where you upsample the the data that you get from like Burmese or the languages that don't have as much. They might not do that during language model training, but they'll do it during tokenizer training to get reasonable things. Another problem is arbitrariness. So let's say we have ES and ST, but we don't have EST in our vocabulary. Should we segment as EST or EST? It's not super clear, right? Like they're both similar. And this happens all the time when you're splitting things into subword tokens. A workaround to this is something called subword regularization, which was also proposed together with the sentence piece paper. And basically what it does is it samples at training time. So you just sample different segmentations so you have good coverage of all of them and you don't necessarily take the highest scoring one. And this is particularly useful when you get data outside of your original training data. So it helps with domain robustness. Cool. Another multilinguality concern is, like, as I mentioned, English is a very kind of boring language with respect to how we do conjugation. Does anyone speak a language where we might have lots of trouble if we segmented just by splitting words into pieces? Any ideas? Some examples of this are Hebrew and Arabic. Hebrew and Arabic both have something called infix morphology, where the center of the word can change when you conjugate. There are very few examples of this in English, but one example is goose, geese. So the G and the SE don't change, but the center OO and EE do. But this happens all the time in some languages. So if you do that, then these just get broken apart and become weird. So you have trouble. So sometimes more sophisticated methods might be more useful. Cool. Any questions here? Yeah.
How are like white space characters handled in these models?
Oh, great question. So how are white space characters handled? Traditionally, the way they are handled is you count the vocabulary by splitting on spaces or splitting on white spaces and segment up like this. But this becomes a huge problem when you start talking about doing something like modeling Python, for example, because white space is super, super important in Python. So nowadays, the white space characters might be either included because you can treat white space characters like any other character and just, learn a vocabulary with white space characters. Or the more common thing to do now is to kind of model the non-white space characters and the white space characters separately. So you have a subword vocabulary where you cover the white space characters. And like, if you look, I think if you look in, let's see if I can actually reproduce this in the GPT tokenizer. So I will do for I in range 3, for J in range 10, print I, J. So you can see eight white spaces are a single token. So they have done this, I think, primarily because they wanted to be good at modeling code. So yeah, that's something they do. I'm actually surprised that like these things are not single tokens, but maybe that's a historical relic or something like that. Cool. Any other questions? Yeah.
During the arbitrary hunting, like during training, you said we sample from different distributions.
Mhm.
During inference, how do you break it? Like, do you break it greedily or like ESTs, would you break it as?
Okay, yeah. So the way you do tokenization at inference, it depends on whether you're using something like BPE or unigrams. So BPE, basically what you do is you do the merge vocabulary things in order, and you just merge together the existing vocabulary items. So like at inference time, you would first split it into characters, and then you would merge together the first vocabulary item, which is ES. Then you would merge together the second vocabulary item, which is EST. So that's what you do for BPE. The unigram model, here, usually you find the segmentation that maxes the unigram probability, and there's a dynamic programming algorithm that allows you to do this. So, yeah. Cool. Yeah.
For BP, how do we decide how long do we want to merge and
Yeah, great question. So for both of these, you need to pick a vocabulary size that you want. And usually you pick, like 32K or 64K or something like that. Llama
And Llama 3 is
256, right?
I think it's
Something like that.
132,000.
132, yeah. So
They're using the same token.
yeah, so recently the vocabularies have gotten a lot bigger. So people have been using bigger vocabularies, probably because it gives you better modeling. Also because models have become more multilingual, so people care about that more, and you need more tokens if you do multilingual. Cool. Any other? Okay, cool. So next I'd like to move on to continuous word embeddings. So the basic idea behind continuous word embeddings is that previously we represented words with a sparse vector with a single one and lots of zeros. If our vocab size was 32K, we would have 32K or 31K 999 zeros and 1 1. what continuous word embeddings do is instead they look up a dense vector that's a lot smaller. So the dense vector could be 512, 768, whatever size. And so the vector itself is a lot smaller, but each element of the vector can be non-zero. So this gives you a lot more information. And so let's say we wanted to use this in a text classifier. The simplest extension of a text classifier is something called continuous bag of words. And the way this works is you basically look up not sparse embeddings, not one-hot embeddings, but dense embeddings like this. You add them all together, and this gives you a sentence embedding for the whole sentence. And then you multiply the sentence embedding by a matrix and add a bias, and that gives you scores for whatever classification task you want to do. So if it was binary, you'd only get 1 score. If it was 5 class, you would get 5 scores. So that's in contrast to the bag of words model. If we think about this, what do the word vectors represent? Basically, the word vectors, we don't really have any guarantee about what they represent. They can represent whatever they want or whatever they are learned to represent. But in general, words that are similar in some way are close in vector space. So a lot of people say this is like, quote unquote, semantic similarity between words. It's not necessarily semantic similarity because semantics, does anyone know another name for semantics? Or, yeah. Meaning, yes, very good. You found a semantically similar word. So, so it means the same thing, right? But they could also be syntactically similar, but meaning-wise very different. So, for example, decided and exploded might be very close to each other in some dimensions. They could also be semantically opposite, but semantically opposite words get very similar vectors. So like love and hate get very similar vectors. So it doesn't necessarily mean that because they're close, they're synonyms. Another thing that is commonly the case, but not always the case, is that each vector element is a feature that has some sort of interpretable kind of meaning. And so, for example, this could mean like one node in the vector or one element in the vector could indicate that something's an animate object. Another could indicate that it's a positive word. And so we end up getting something like that looks a little bit like this, where one dimension could be the the sentiment polarity, like very good things are up here, very bad things are down here. The other thing could be animacy. So inanimate things are over here, animate things are over here. So this is shown in 2D, but in reality, we use like 512 or 1024 or other things like that. Cool. I'd like to give a note about when I say look up a vector. So what does looking up a vector mean? Basically, what it means is we're grabbing a single vector from a big matrix of word embeddings. So we have this big matrix like this with rows equal to the number of tokens in our vocabulary and columns rows equal to columns equal to the number of words in the vocabulary, rows equal to the size of the vector. And if we look up number 2, we might be grabbing the third index from here, the third vector from here and taking it out. That's actually equivalent to multiplying by a one-hot vector. So what that means is we could be taking this big matrix and multiplying it by a one-hot vector. And that gives us exactly the same result. There's advantages to looking at this both ways. So there's there's advantages to looking at this both ways. What's the advantage of the first one? And I kind of showed it on the screen, so you might already know.
Time complexity.
Time complexity, yeah, exactly. So this is time 1, whereas this is time n, basically, in the size of the vocabulary. Can anyone think of advantages of this one? Memory? Yeah.
Look at a sentence, you can just have a bunch of one-hot vectors and you just get a full sentence.
Yeah, if you want to calculate the embedding for a sentence, you could add together a whole bunch of one-hot vectors and then calculate for this sentence. Yeah, that's one advantage. That's not exactly what I was thinking about, but it's a good point. Parallelization. Yeah, maybe that's kind of similar to the other one too. Yeah. One advantage of this is actually you don't need it to be a one-hot vector. It could be like the vocabulary vector, but it could also be a vector that says, I want half of a cat and half of a dog. And that would allow you to kind of get a cog or a dat or something like that. And basically, this is interesting because if you're learning, you can do things like predict the probability of the next word and multiply by the probability of the next word, which would allow you to kind of mix together vectors and do gradient-based learning on vocabularies and stuff like that. So knowing both of these interpretations can be useful. So now let's move to training a more complex model. Again, this will be review for a lot of people if you've talked about neural networks, but I'll go through it pretty quickly, or if you've learned about neural networks. So previously, we learned the bag of words model using an algorithm called the structured perceptron. It was extremely simple. We could implement it in several lines of Python. And just to remember for review, what we would do is we would make a prediction. And if the prediction was wrong, we would multiply the feature vector and by the label and move in that direction, essentially. So we want to generalize this, though, because this won't work for every single model we have, every single loss function we have. So what we will do first is we will take this algorithm and we'll generalize it using gradient descent. And so basically the way gradient descent works is we write down a loss function and we calculate the derivatives of the loss function with respect to the parameters and move the parameters in the direction that reduces the loss. And a couple loss functions that we use for things like binary classification include the hinge loss and the sigmoid plus negative log likelihood loss. So the hinge loss looks a little bit like this. It's a loss where, for example, this is one variety of the hinge loss. It's the simplest variety, where if the label is 1, we have a loss if the input value x is less than 0. And if the label is -1, we have a loss if the input value x is greater than 0. And so another way to put this is if we make a mistake by saying something that has a label of 1 gets a score of less than 0, then we get a loss. And if we make a mistake by saying something with a label less than 1 has a score more than 0, then we also get a loss. Another example is the sigmoid plus negative log likelihood loss. And the sigmoid is a function that looks like this. And the negative log likelihood is we take the negative log of the sigmoid. And what this results in, oh yeah, sorry, I didn't actually write the sigmoid function, but basically it looks like this. It's a function where the slope around 0 is large, and that's the tangent. The slope around 0 is large, and it's between 0 and 1. And so this negative log likelihood basically is very similar to the hinge loss. You can see the shape is similar, but the thing is it doesn't suddenly become 0 right at 0. So it doesn't become 0 if you don't make a mistake. And so what that means is for the hinge loss, if you don't make a mistake, you won't make any changes, or your loss will be 0, and that basically means you won't be making any changes to the model. But the sigmoid, no matter how good your probability is, you're still going to continue updating the model. So that's the big difference between these two. Then based on this, what we do is we calculate the derivative of this function. If you want to derive this, you can. Or no, okay, sorry, this is the hinge loss. So for the hinge loss, it's actually not too hard to derive this. This is the hinge loss. This is how we calculate our score. And then if we calculate the derivative with respect to Wi, in this sum here, everything other than Wi doesn't have and will have no effect on this derivative. So basically we can throw away everything except Wi, frequency Vi, X. And based on that, we get minus Y frequency Vix if this value is greater than 0, if the loss is greater than 0. If the loss is not greater than 0, the max on the other side becomes 0, and so our derivative becomes 0. So basically, our derivative is 0 if we don't make a mistake, and if we do make a mistake, then it becomes non-zero. Then to optimize parameters, what we do is we do stochastic gradient descent, where basically we take steps in the direction that reduces the loss. And so GT is our gradient, and we take the gradient of the loss, and then we move in the direction that lowers this GT. So that's why we're subtracting here. And then we have a learning rate, eta. And so this learning rate could be 1, it could be 0.1, 0.01, et cetera. There's many other optimization options. So I have a survey of various optimizers in the references if you want to learn more, and I'm going to talk about Atom in a second. But this is a basic idea. Now, the reason why I wanted to introduce the structured perceptron algorithm first is the structured perceptron algorithm is a very good intuitive algorithm where you can kind of totally understand what's going on in Python, but it's actually a special instance of gradient descent. So can anybody link this algorithm to the concepts that I just talked about before? Any ideas? So which loss function would we be using here? Yeah, the hinge loss. So we're using the hinge loss. Any ideas about what the learning rate might be? 1. Yeah, exactly. So we have a hinge loss and we have SGD with the learning rate of 1. So you can see that this is it's essentially a special version of gradient descent. Typically, what we do nowadays is we don't use the hinge loss very much anymore. If we're training a binary classifier, we almost always use the sigmoid. There's 2 reasons for this. Does anyone have an idea what these might be? Differentiability. I just differentiated the hinge loss though, so. Yeah. But you're close, but not exactly, yeah.
Gradient descent won't work when the loss is flat.
Gradient descent won't work when the loss is flat. Pretty close. Gradient descent won't do anything when the loss is flat. So the loss isn't flat every time. It's only flat when you don't make a mistake, but you would like to maybe move in the direction when you're, even when you're not making a mistake. There's one other reason. Yeah. Mm-hmm. Yeah, that's similar to what we were talking about before. Like when you're not making a mistake, you still reinforce your positive examples. But yeah. Overfit the noise in the training data with hinge loss?
Because something wrong, like there's noise and it's kind of like fitting the loss very tightly to the noise.
Mm-hmm.
You're not gonna like adjust.
Yeah. Overfitting to noise. I think that's also actually a problem with the sigmoid, but it might be a little bit less of one because it's smoother and also looks at the positive examples. Yeah.
To which you correct the model is the same, no matter if it's slightly wrong or even largely incorrect.
Yep.
You want to fix that. That's why sigmoid is there.
So the rate at which the model changes is the same regardless of whether it's slightly wrong or very wrong. That might result in better training stability. It's not what I was thinking of, but yeah.
Like
where the this data point is correct, we ignore it.
Yep.
And then the other data point makes a flip, and then now that one is correct. And the other one.
Yeah. Could it oscillate between different solutions? Yes, but that's a problem of stochastic gradient descent or even gradient descent overall, more than a function of these particular loss functions. Yeah.
Zero for only a vanishing gradient problem, exploding gradient problem.
Vanishing or exploding gradients. Yes, that's a big problem, but it's a problem everywhere. Sorry, everybody's talking about optimization, and this is actually not an optimization problem. Yeah, any other ideas? Yeah. Is it a momentum issue? No, momentum actually you can introduce with either one of these. Okay, these are all great responses. They demonstrate a good understanding of machine learning, and thank you everybody for them. Actually, the reason why people use the sigmoid more is because it gives you an idea of probability. So it gives you a number that's between 0 and 1 that can tell you like with which confidence a particular answer is correct, whereas the hinge loss is not a probabilistic one. So yeah, sorry, I talked only about optimization and kind of gave a difficult question there. So yeah, apologies for that. Yeah.
What kind of classification task are you thinking about?
This could be any type of classification. I'm mostly talking about binary classification here because you need a different function if you're doing multi-class classification, but anything where the answer is yes, no.
But like, in general, I haven't seen probably this much in vision side. It's more on the side. That's what like what kind of tasks
so you haven't seen binary classification in vision?
I mean, is it like hinge loss is used for any particular task?
Hinge loss.
Like any example that.
So hinge loss can be the biggest place where hinge loss is used nowadays is in featureized models in tabular data. It can be used in optimizing models through methods that are like reinforcement learning. There are not a lot of people using it nowadays, but I think it's more a function of people not knowing about these as much or not considering them as much. And also possibly because people want probabilistic estimates of the output. I don't think that necessarily means they're worse. In fact, in rigorous like examinations of which methods to use, actually hinge loss fares pretty well. And so I agree that this is not very widely used. The main reason why I wanted to introduce it is because it gives the intuitive connection with, you know, the very simple optimization algorithm. Yeah. Cool. Great questions. Let me move on though to make sure we get through everything that I wanted to talk about today. So for combination features, basically are things like, I don't love this movie. There's nothing I don't love about this movie. So all of these, you know, the words in here are not super indicative of whether this is positive or negative, but when you combine them together, it makes a big difference. So the basic idea of neural networks, like I talked about last time, is we throw all of these vectors into some complicated function to extract combination features. And then from that, calculate scores. A very, very simple example of this is something called deep continuous bag of words. And the way this works is you have a continuous bag of words model like we talked about before, but instead of just calculating the scores through linear transformations of these features, we run them through nonlinear transformations, through matrix multiplies and added biases. These are called linear layers in most neural network toolkits nowadays. And then we have some sort of nonlinearity like the tanh or the ReLU or the swiglu or other things like this. And this gives you these features. These are intermediate hidden layer features. We might do it again. And then based on this, we do a similar multiplication and calculate scores and probabilities. So if we look at one thing I should point out is these methods here are kind of like ridiculously effective. They're way, way more effective than you would think they should be. Even if they are completely ignoring word order or other things like this, just because they can very effectively count all the words and kind of guess what the original sentence was, despite the fact that you scrambled the words in the sentence. So there was a paper from a while ago that demonstrated that this was competitive with the best state-of-the-art models at the time. Of course, now transformers are the state of the art, and this would not come anywhere close to a pre-trained transformer model. But still, every once in a while, we see kind of these order agnostic models getting much better results than they should be able to get. Okay, so what do our vectors represent nowadays? So we can learn feature combinations. So for example, a node in the second layer might be that feature 1 in the word embedding and feature 5 are active. And if feature 1 is something like indicating a negation word, and feature 5 is indicating a very negative sentiment word, this could capture things such as not and hate are included in the input. And so this means that you can count different types of words. You can combine together counts of different types of words, basically anything like this. The way we express neural nets, again, this is going to be very brief because I assume that many people have seen this in a machine learning class. If you haven't, and this is new to you, you definitely should go to the TA recitations on things like PyTorch and other things like this that we're going to be having. They aren't announced yet because I just allocated them yesterday, but we will be announcing them very soon. And basically what this will entail is go to office hours and we'll have a quick walkthrough of like toolkits that we use like PyTorch or Sentence Piece or things like that. Yeah.
Before we go on to this,
yes.
How are dense vectors initialized versus like 1 over 10 coding was quite intuitive? How
yep.
are dense vectors initialized?
How are dense vectors initialized? So in neural nets, all vectors or matrices that we create are usually initialized randomly. Sometimes they're initialized to 0, but usually initialized randomly. And they're initialized within a scale that is appropriate for getting good gradients at the very beginning of training. And I think I'm going to talk about it a little bit more today. So a neural network is originally inspired by the brain. I think this is one of the big kind of triumphs of studying human, the ways humans do things and mimicking the ways humans do things and like actually being successful at building better machine learning models. Very often we build human-inspired machine learning models and they're not any good, and just throwing something in a big matrix multiply does a lot better than the human-inspired model. But this is one example where it really worked. But we've kind of moved away from really strictly mimicking to how the brain works to just having differentiable graphs of computation or computation graphs. So a computation graph, basically, we have nodes in the graph. And a node is some set of values. It's usually a scalar value, a vector, one-dimensional vector, two-dimensional matrix, or arbitrary dimensional tensor. Nodes can also be functions. And the result of this is, a tensor. But the function can have inputs. And the edge is a function argument. And also a data dependency. And the node with an incoming edge is a function of the edge's tail nodes. So these can be, unary or binary, trinary. You can have as many incoming edges as you want. You can also have 0, like in this original one here. Every node knows how to compute its value. So it has a function that you can compute. So that would be like U transpose. And then you could also calculate the argument or the edge value times the derivative of an arbitrary input. So that's useful for backpropagation, which I'm going to get to in a second. So computation graphs are generally directed and acyclic. And Another important thing is there's multiple ways to implement computation graphs. This is actually really, really important. It's a really important fact. And if you're not thinking about this, you should think about it carefully. And the reason why it's important is this computation graph and this computation graph calculate the same thing. This does U transpose a matrix multiply and another matrix multiply. This one here has a special operator for xt transpose AX. And the reason why this is useful is because, number one, this is kind of a known derivative. It's something that we know how to calculate the value of, and there's shortcuts where we don't have to do all of these steps. Another thing is, in contrast to this and this and this, where we had 3 nodes, now we only have 1 node. And so this is a much simpler graph on the right. What this means is savings of time and memory. And memory is the more important one if we're running things on GPUs, for example. Because if this uses 1/3 of the memory of this one, then you're going to be very happy about that because you're going to be able to fit a bigger network on your GPU or other stuff like this. So how exactly does this manifest itself? For example, in PyTorch, PyTorch or any other neural network toolkit, the most common example of this is when you calculate, for example, a hidden unit. You could do this by WX plus B, or you could do this by linear. This is not exactly the syntax you use, but it should be clear. Or you could have this function linear WBX. And linear is like a single function. This is a matrix multiply and then an addition. So this takes twice the memory for the hidden state that this one would take, because this one can be done all in a single pass. So there's other examples like transformer. So transformer, we're going to talk about in a few classes, is rather complicated, but if you use a highly optimized implementation, it'll be much, much faster. In the end, we can also have assignment in these computation graphs. The assignment is basically, all it's doing is labeling a node. So all of these intermediate nodes are calculated, and their values are typically stored in memory. So if you have a really, really complex function, normally in Python, it would only take the memory of the final expression here, and all the other stuff would just disappear when you're done calculating it. But in the computation graph, you keep all the intermediate results around. So that's also important to be aware of. Any questions about this? Yeah. What's the advantage of keeping the intermediate steps? Let me talk about backpropagation, and then we'll get back to that. So we have algorithms. We have graph construction and forward propagation. Graph construction is basically where you create the graph. And forward propagation is where you actually calculate the values in the graph. So let's say we finished our graph construction step. The next thing that we can do is we can actually calculate the values. All of these are inputs, so we know their values ahead of time. And then we do a topological sort of the graph and find all of the ones that don't have any uncalculated inputs. And we can calculate those in arbitrary order. So we calculate that one. Now we can calculate either of the blue ones. We calculate that one, that one, that one, and then we're done, basically. Another thing is you actually can calculate both of these at the same time. This can be parallelized. And a lot of neural network toolkits are actually doing that under the hood if you're not, if you let them. Number two, so we also have backpropagation, and backpropagation is a really important part why we need to use computation graphs. We process examples in reverse topological order, could just be the opposite order that we did the forward pass in. And we calculate the derivatives of the parameters with respect to the final value. Usually the final value is a loss function we want to optimize. So we'll usually have a single final value that we want to minimize, and then we do the parameter update. Um, so backpropagation, we start at the end. This is the final value, and then we move back in reverse topological order like this. So now the question is, why do we need to keep the intermediate values? Very good question. The reason why we need to do this is the result of this node of like the intermediate nodes depends on the gradient here and the gradient in the following node and the value here. So in order to calculate this value, in order to turn that node red, you need to know both of those values. So you need to save the intermediate values. There's also methods called checkpointing, where checkpointing basically what it does is it forgets some of these values. It forgets some of the intermediate values and recalculates them. It's when you do backprop. And this is a way of saving memory at the cost of more computation, basically. So that's another thing that you could do. Cool. So I have a few concrete implementation examples. I might not actually walk through the code here, but there's basically two reasonable options for implementing neural network models nowadays. Actually, there's three. There's three reasonable options for implementing neural network models nowadays. The first one is PyTorch. This is what 98% of the people in this class should probably be using. Then there's JAX. I wouldn't say 98. Maybe 90, 95. You can be. I'd be happy to have 5% of adventurous people. So PyTorch was developed by Fair and Meta. JAX was developed by Google. A good reason to use JAX is you're working at Google. Good reason to use PyTorch is you're working anywhere else. So PyTorch is by far the most widely used in NLP research outside of Google. JAX is used in some NLP projects. PyTorch favors dynamic execution. And what dynamic execution means is basically, in many cases in PyTorch, not all cases in PyTorch, but in many cases, you essentially redo, we redo this graph construction step every time. So every time we process a new example or a new batch of examples, we reconstruct the graph. And while we are reconstructing the graph, we calculate the forward examples or forward values. The opposite of this is definition and then compilation. And the way this works is you define the graph only once. And so you define the shape of your network. And then when you define the shape of your network, then you just use it over and over again. You throw more data at it and then just continue using the same one. The PyTorch supports kind of definition and compilation. JAX kind of supports dynamic execution. TensorFlow does, but you probably don't use TensorFlow nowadays. But the advantages of these is this is more flexible. So you can do things like you can just use Python control flow when you are executing a PyTorch program. So you can calculate something according to your neural network and then have an if statement where if the value is greater than 0, then you do this. If the value is less than 0, you can do this. So that's very useful in some cases. The good thing about definition and compilation is you can create like a very, very efficient graph. You can spend lots of time compiling the graph, maybe even generating custom GPU code. And then that means that afterwards, it'll be really fast to continue using. PyTorch definitely has a more vibrant ecosystem, although there is some stuff in JAX. I said there are three options. So I'd say this is the 95% option. This is the 4.9% option. And then if you want to be the 0.1% option, you can actually write GPU code yourself. And like, if you're a student here and you want to learn, this is not a bad learning experience because if you are able to do this, this will put you in the 0.1% of people that know how to do this. And that allows you to create the like absolutely most efficient code for doing, whatever you want to be doing. And like a lot of the large language model training companies, for example, have put a very high premium on being able to do this. So you could do that. If you're interested in doing something like this, there's a library called Cutlass where you can take a look at this at various algorithms implemented in CUDA code. But as I said, that would be like only if you're super interested in efficiency and engineering that way. Yeah.
Are there any memory or time trade-offs for using PyTorch as dynamic execution, like while training or inference?
Any what time trade-offs?
Because it has dynamic execution.
Oh, memory time trade-offs. Like in all of these, there's memory time trade-offs that if you get to that point, you can think about them.
Compared to JAX, it doesn't say more.
Yeah. So one big advantage of JAX, in addition to just the speed overall, is JAX thinks about like everything in tensors, and because it thinks about everything in tensors and in a kind of very structured way, it also makes it easier to do multi-GPU things. So you can split the tensors across multiple GPUs and train with them. And that's actually quite a bit simpler than doing it in PyTorch. I'd say in terms of memory time trade-offs, JAX is probably going to be more efficient most of the time if you program both of them right. But there's lots of good examples in PyTorch that you can work with, and also just it's going to be simpler to do a lot of things in PyTorch. So that's the reason why most people favor it, I think. Cool. Yeah. Oh, are there libraries to help go beyond CUDA GPUs? Yeah, there are. I've only done CUDA myself. Actually, that's a great question though. Has anybody done multi GPU vendor GPU code writing? I'm actually kind of surprised if we have 130 people in this class and 0 people who've done that. But yeah.
So I think the basic difference, if you use PyTorch, for example, if you input your model, for example, we usually use the model .2 to the CUDA. That's all the way we use it. But if you use the AMD or use the Apple, for example, you just change the CUDA to the NPS setting. But you need to check the PyTorch. I think there's support is for different files and different functions. I think not all the functions will support by NPS or AMD. But I think all the work you need to do is through your compile and all the setting part. But rather than you're writing your actual code, because the only thing you need to do on your code is to change the .2 function to .2 to the CUDA or .2 to NPS, .2 to AMD or CPU or whatever you want.
Yep. So this is a good point. I'll repeat it because the people in the back almost certainly didn't hear it. But like if you're using something like PyTorch or JAX, it's quite easy to use other varieties of hardware. You can use your CPU. If you're on Mac and you have a Mac like M1 or higher with Apple Silicon, you can use MPS. If you don't know what MPS is, it's basically the acceleration, like the native GPUs on the Mac hardware. It makes things a lot faster. You can actually like train models on your Mac. It will get very hot. So don't put it on your lap or something. Like seriously, it will get very hot, but it will train, and that might be a good alternative to using GPUs. I think the original question was though if you actually want to write kernels. So I don't know the answer to that. I do know that one of the top projects for doing multi-GPU stuff is actually created here at CMU, MLC, by Tianqi Chen's group. So you can take a look at MLC, but I don't know if that would be the recommended way of doing it because it's even going farther. It's like compiling things into executable programs. But I'll try to learn a little bit more about that. I should have an answer for that, but I don't. So yeah, basically, when you're training a model in a neural network framework, you create a model. For each example, you create a graph that represents the computation that you want, calculate the result of the computation, and if training, perform backprop and update. I have a bunch of examples of doing this in PyTorch. These are intentionally made to be extremely simple examples. They're not programmed in an efficient way, but they're programmed in a very easy to understand way. There's lots of examples of how you can program things in more efficient ways. So this is really like bare bones. So we have examples of the bag of words model, the continuous bag of words model, and the deep continuous bag of words model. I'd like to cover a few more important concepts as well. Better optimizers. So SGD is one optimizer. In reality, nobody uses SGD anymore. Or very few people use SGD anymore in natural language processing. Almost everybody uses Atom or some variant of Atom. Atom is the most standard optimization option, and it fixes two problems in SGD. The first one is instability, and the second one is lack of updates to less frequently used parameters. And so the way it fixes this is it calculates this M term, which is essentially the mean of the previous gradient updates. It's a rolling average of the gradient updates, where beta 1 is how much you keep the momentum, or you keep the previous mean of the updates, and then you add in the gradient to it. This one is the rolling average. Sorry, this is not the gradient. This is the variance, or the squared gradient. So this is taking the rolling average of the squared gradient. And it also has a correction term to prevent bias early in training. So early in training, this value will be very small. And so you have a correction term to prevent it from being very small at the beginning of training. And so the final update rule looks like this. And the important thing about this is you are not multiplying by the gradient. You're multiplying by this rolling average of the gradient. The problem that this fixes is this fixes the problem of instability. So instead of like jumping around a lot, you move much more smoothly because the gradient doesn't change a whole lot every time. And this is the variance, and you divide by the square root. You divide by the square root of the variance. What this does is things that don't get big gradient updates, when they get things that don't get big gradient updates, when they get a gradient update, the gradient update has a bigger effect, essentially. So if the gradients are very small, you still move it more. And so the reason why this can be helpful is, just to give one example, let's say you have a very rare feature that only fires once in every 1,000 times or something like that. If it only fires once every 1,000 times, this will become much smaller. And so that allows you to update it a lot more the one time it does fire. So it allows you to spread your updates well among all the features. So this is really important. There's Atom. There's also Atom W, which is a corrected version of Atom with weight decay, which is a variety of regularization, but I'm not going to get into that in this class. The next thing is visualization. So like I showed a fake visualization of embeddings before, but there are better ways to visualize embeddings. One way that you can visualize, but the embeddings are like 512, so you need to turn them into something that you can actually see, like 2D or 3D are the two things that humans can comprehend. And so actually 4D we can comprehend too if you do it in time. I've never seen a video visualization of embeddings through time or something like that, which would be interesting. But yeah, anyway, so you need to reduce it to a smaller number of dimensions. One way you can do this is through kind of linear rank reduction through something like principal component analysis. And this is an example of principal component analysis of word embeddings from a really long time ago by Mikolov. And basically what you can see is after you do this decomposition, you find interesting linear relationships between embeddings. So for example, almost all of the time, you can have like a country over here and its capital over here, and the vector between them is going to be similar. So this is pretty cool, right? Because what you can do is you can calculate this like country to capital vector and kind of guess what the capital of a country is just from word embeddings. The problem with this, though, is it actually isn't super intuitive to visualize a lot of things. And this is just an example where people took the pixels in handwritten characters and did a PCA over them and visualized them on 2 dimensions. And you get this very blurry thing where a lot of the numbers blur together. And so despite the fact that if you actually looked at the images of the numbers, you would be able to tell the difference between them. They blur together when you do this sort of linear decomposition. So there's also nonlinear methods. And what these nonlinear methods basically do is they train an autoencoder style neural network where it downweights it downsamples to like 2 dimensions, does a nonlinear projection, and then upweights, upsamples again. And the objective function is created so that the similarity or the closeness of the values here is similar to the closeness of the values in the high dimensional space. And so this gives you much more crisp visualizations of things in low dimensional space. So if you want to do a visualization, this is usually the preferred way of doing this nowadays. But there are some caveats. Because you're doing this, Tisney actually has, Tisney is the name of the method. Tisney actually has some hyperparameters. And if you change the hyperparameters, you can get wildly different results. So this is like the actual original data in 2 dimensions. And then they ran it through Tisney and got this and this and this and this and this, depending on the hyperparameters that you use. This is another one where you just have things in a line. You get things that are very weird, breaking off, somehow reinventing DNA, and stuff like this. So probably the things that are close together are still close together in most of these things, but just you need to be aware that weird things can happen. Another thing is, like, while I'm on the topic here, I don't actually have it on the slides, but another way that people do this pretty frequently, or try to interpret neural networks pretty frequently nowadays, is through sparse autoencoders. And this is an example of this is an example of something that was created by Anthropic, the company that makes Claude, and basically they interpreted the features in their language model. Actually, I think this is not. Sorry, this is not the one that I was looking for. Okay, well, but they have a nice blog post recently where they do interpretation of language model features. And the way this works is instead of going from a dense vector down to like 2 dimensions so that you can visualize it yourself, they go from a dense vector up to a very large but sparse vector, so that each of the things kind of gets assigned to features. And when you make it very large but sparse, the features become more meaningful. And so you can look through each of the features and kind of understand what's going on. So sparse autoencoders is another way that people tend to do this sort of interpretation type thing. Cool. So yeah, that's all I had for today. It's kind of high level for a lot of things. Were there any questions before we finish up? Yeah. Oh, yeah, sorry, the AWS quiz. I'm going to tell you about 2 pieces of compute credits that you get as part of this class. The first one is you will get up to $150 in AWS credits. AWS credits are good mostly for getting GPUs if you want to train a model. It's not a lot of money, but it's maybe better than nothing. we want you to apply for these credits by Thursday. And so what you need to do is you need to go sign up for an AWS account and fill in your 9-digit or 9-digit AWS account or 12-digit. 12-digit AWS account in the quiz. We will try to get you credits as soon as possible. The moment you get the credits, try to use a GPU machine. And the reason why I say the moment you get the credits, try to use a GPU machine is because you might try to use a GPU machine and realize you don't have permission and you have to ask for permission. And asking for permission can take some time. So doing this as soon as possible is a good way to make sure that you have it in time for the first homework. The other piece of credits that we're going to give you is 50, I'm not sure if it's $50 or $100 of OpenAI credits. And this can be used for querying things like GPT-4 or GPT-4 Mini or things like this. We're going to do that a little bit later because you shouldn't need it for the first assignment, but we'll give you that as well. So yeah, that's the explanation of that. Well, the wait list will be cleared by next week. Yeah. So if you're on the wait list, we will be clearing the wait list until the ad deadline. So as people drop, we will continue clearing the wait list. If by the ad deadline you're not off the wait list, then you will be able to get off the wait list.